Making sense of QFT. Lecture 5. Quantum Electrodynamics. Here is the outline. First, we will simplify quantum electrodynamics to the point permitting sensible calculations even in the framework of our short lectures. The main theoretical tool in quantum field theory is the S-matrix. And we will see how S-matrix can be computed within Dyson's perturbation theory. Another simplification comes from Feynman's diagrams. Our first QFT calculation of an experimental effect will be the electron-electron elastic scattering amplitude. We will also find out that the theory predicts a spurious effect of electron self-scattering. This is an invitation to renormalization, which will be the topic of our next lecture. Recall that in the last lecture, we were able to formulate relativistically invariant quantum electrodynamics. We constructed 10 generators of the Poincaré-Lie algebra and built our interactions from this product of quantum fields. Today, we will begin extracting physical predictions from QED and comparing them with experiment. Our plan is to focus on big ideas, so it will be helpful to simplify the notation as much as possible, hopefully without losing its key features. In our expression for the potential energy, we will drop integration sign, indices, and numerical factors. In addition, we will replace quantum fields with sums of creation and annihilation operators. By the way, the subscript here, and in what follows, is the order of perturbation theory. This subscript, in our case it's 1, is equal to the power of the electron's charge in the product. In dimensionless units, the electron charge is much less than unity, therefore terms of higher perturbation order usually have lower physical significance. We get a further simplification by ignoring the presence of positrons and removing from consideration all terms containing positron creation and annihilation operators. We will also ignore spin components. After all these steps, the Hamiltonian of QED takes this simple form. H0 is the familiar energy of non-interacting electrons and photons. The interaction Hamiltonian V1 is a sum of two terms, V1A and V1B. As you see, and unlike in ordinary quantum mechanics, the interaction here changes the number of particles. The first term can be interpreted as absorption of a photon by a free electron, and the second term is spontaneous emission of a photon. Such processes by themselves never occur in nature because they violate momentum energy conservation laws. One of the most important quantities in quantum field theory is the S operator, which is frequently named the S-matrix. 95% of all efforts in QFT are spent on calculation of the S-matrix. The primary goal of the S-matrix is to describe a class of physical experiments known as scattering experiments. They are the major tool for studying subatomic world. Here is a simple example of experiment with electron-electron scattering. At time t in the past, the two electrons were free and non-interacting. Then they came close to each other at time around 0, and in the interaction region they experienced acceleration and had an opportunity to create extra particles, such as photons. Then all particles left the interaction region and continued to propagate without interaction again. This was an exact description of scattering. In quantum mechanics, it can be achieved by applying the full interacting time evolution operator to the initial vector state. However, such dynamical calculations are extremely difficult. To make their life simpler, physicists invented a remarkable approach called scattering theory. Note that while the particles are outside the interaction region, either before the collision or after it, their dynamics is well described by the non-interacting Hamiltonian H0. The corresponding time evolution calculations can be done very easily. In addition, we can assume that the interaction region is very small and all changes occurring there happen instantaneously. So the abrupt change of the state at time 0 is achieved by applying a single operator S, which is called the S matrix. Then instead of the exact description of the time evolution with the full Hamiltonian, we can represent the history of collision in 3 steps. First, there is a time translation from time t in to 0 with the non-interacting Hamiltonian. Then the resulting state at time 0 is multiplied by the S matrix. And after that, the system continues its non-interacting evolution from time 0 to infinity. In this approach, all non-trivial scattering effects have been condensed in the S matrix. If we manage to calculate the S matrix, we'll get access to 2 important pieces of physical information. First, from the numerical coefficients of S matrix terms, we can calculate scattering cross-sections comparable with experiment. Second, we can also obtain energies of bound states. But this step would require analytic continuation of the S operator in the complex energy plane. In this graph, I have shown schematically the function S of E in the plane of complex energies for the case of electron-positron interaction. Strictly speaking, the S operator is defined only when colliding particles have non-zero kinetic energy, or the total energy is greater than the sum of particle rest energies. In other words, the physical range of scattering energies is the green portion of the real energy axis. However, we have also the right to continue this function analytically to the complex plane, in particular to the entire real axis. It can be proved that this function will have poles exactly at energies corresponding to bound states in the system electron plus positron. The locations of these poles are shown by red crosses on the graph. Many convenient mathematical tools have been developed for calculations of the S matrix. In our lectures, we'll adopt the simplest perturbation approach known as Dyson's formula. In this formula, V of t is the interaction operator sandwiched by operators of non-interacting time evolution. Next, we introduce further simplification to the Dyson's formula. This is a perturbation series. In the zeroth order, the S matrix is equal to 1. And the magnitude of each term decreases as its perturbation order increases. So we hope to get a reasonable accuracy by considering just few low-order terms. To simplify our notation even more, we remove all extra integration signs and leave only the leftmost t integration from minus infinity to plus infinity. Of course, in this simplified notation, we will not be able to conduct realistic calculations. However, we'll keep the minimum mathematical structure required for qualitative analysis. In order to perform t integrations, we must know the t dependence of the integrands that are products of creation and annihilation operators. T dependencies of these operators are shown on the right. Then a very important conclusion follows about the structure of operators under the T integral in the S matrix. The T dependence of any operator is given by a numerical factor, an exponent where E is the so-called energy function, which is the sum of energies of created particles minus the sum of energies of annihilated particles. Then the T integral in each term of Dyson's formula can be easily evaluated. Each S matrix term becomes a product of the operator part and energy delta function, which expresses the requirement of energy conservation in the scattering process. Now return to the first order S matrix. Using the acquired knowledge, we calculate S matrix contributions as products of operator factors and energy delta functions. Arguments of the delta functions never turn to zero because this is forbidden by the energy conservation law. This means that the first order contribution to the S matrix vanishes. Now, let us turn to a more complicated calculation of the second order S matrix, which is a sum of 4 terms. We will focus on the second term in this expression. Its analysis will be more convenient if we rewrite this product of creation and annihilation operators in the so-called normal order, in which all creation operators are on the left and all annihilation operators are on the right. This means that we have to move creation operators to the left. But this operation is non-trivial because operators do not commute with each other. Permutations of operators produce extra terms according to their commutators and anti-commutators. Of course, we can do this calculation manually and arrive at the result, which is the sum of 4 terms. But this was just the simplest case. For higher perturbation orders, calculations become tedious and boring very fast. But there is a way to make them more entertaining. These are Feynman diagrams. The idea is to represent each interaction term by a graph. Then the process of normal ordering can be visualized as a series of graph manipulations. The whole numerical factor of a term will be represented by the graph vertex. Electron operators are represented by straight lines and photon operators by wavy lines. Annihilation operators are lines entering the vertex and having a dovetail on the other end. Creation operators are lines with arrows pointing out of the vertex. With these rules, the two interaction terms are represented by the following graphs. Note that for convenience, I place external graph lines in the same order as operators in the product. Incoming dovetail lines represent annihilation operators and are on the right. Outgoing arrows correspond to creation operators and are on the left. The next question is how to process a product of two diagrams. The famous Wick's theorem says that this product is represented by a sum of diagrams with all possible arrow-to-tail couplings. In our example, the theorem leads to the following four summands. There are no couplings in the diagram A. This is a disconnected diagram which is not relevant to the description of scattering and will be omitted. In the diagram B, we couple electron arrow with electron tail and obtain a graph describing electron-photon scattering. Diagram C with coupled photon lines describes the electron-electron scattering. Finally, in the diagram D, both electron and photon lines are coupled. This leads to the formation of a loop, and the described process can be characterized as a scattering of the electron on itself. Now, if we collect all second-order S-matrix terms, we will be able to classify them into three distinct groups. First is the group of so-called physical terms. Their described processes, such as electron-electron or electron-photon scattering, are physically possible with energy conservation. The energy delta function is non-zero on the energy shell, and these terms provide finite contributions to the S-matrix. Here is the electron-electron scattering diagram in more detail. If we take into account all previously ignored numerical factors, we'll find out that the numerical coefficient of this S-matrix term is proportional to the inverse square of the transferred momentum, k. This result is characteristic for charges interacting with each other by a Coulomb force. So our approximate QED calculation agrees with experimental data pretty well. Return to our classification of S-matrix terms. The second type are so-called virtual terms. In our case, these are processes in which three particles become converted into one particle, or one electron decays into three particles. These events cannot go with energy conservation, so their contribution to the S-matrix vanishes. There is also one renorm term whose energy function vanishes for all values of momenta. The delta function is infinite, so the S-matrix contribution is infinite as well. As we already mentioned, this contribution can be interpreted as a result of the electron emitting and immediately absorbing a photon. It looks like electron interacts with itself even in the absence of other particles. We have never seen this kind of self-interaction in usual classical and quantum mechanics. This is specific for quantum field theory, where particles can be created and annihilated. One problem is that the diagram loop translates into so-called loop integral which diverges and leads to an infinite numerical factor. But this is not the most severe problem. Even if the loop integral were finite, the presence of renormed terms in the S matrix would be unacceptable, because these terms are t-independent. So the t integral from minus infinity to plus infinity is divergent. The only good renormed terms in the S matrix are zero renormed terms. Then we have to conclude that something is wrong with our theory. We will have to review our approach and understand how we got to this unphysical result and what can be done about it. This kind of analysis is made in the renormalization theory. We will talk about it in our next lecture. See you next time. Thank you.